Okay, so let's get started. We're going to be taking a look at working with our acceleration enrichment style tuning in our Link G5 and G4X systems. Our acceleration enrichment is going to be used to characterize fueling delivery for rate of change in our throttle movement. What this means is that as we're driving and we have throttle movement, so our throttle blade's actually moving, we're not in a steady state condition, we need to have additional fuel being added as a proportional amount to the rate of change in throttle. Essentially what we're trying to characterize is as the throttle is opening, so we have a throttle tip-in event, let's say you're making a gear shift or you're coming from part throttle and stabbing the throttle going to wide open throttle, we're going to have a momentary burst of airflow entering the engine. In that situation, we're going to have a momentary lean condition unless we're accounting for the rate of change in our throttle blade movement as the engine is running. Now, the main fuel table will be important that it's dialed in correctly, but it is not going to allow us to characterize this specific situation where we have our throttle blade having larger movements and having those airflow bursts. Let's jump in here and take a look at understanding that a little bit more. So we're going to move from our basics page and jump in here to our fuel page. Now the main fuel table, whether in traditional or the model mode, this represents steady state airflow compensation. So in traditional mode, we calibrate everything, idle, part throttle, wide open throttle. We're not finding we have large throttle blade movements. We have steady state airflow into the engine. In that situation, the traditional mode is essentially characterizing our steady state operation. In the model mode, we know we're estimating the amount of air mass coming from our volumetric efficiency values here in our table, as well as all the other parameters that go into the calculation for our air mass. What we'll find is, again, we're characterizing steady state airflow, or estimating the steady state airflow entering the engine. When we get into those situations where we have a transient condition, so the throttle blade is moving rapidly, we can't rely on the injector pulse width that's coming from our main table or the calculations. That's where we need to ramp up the pulse width in a very specific manner. So it's going to be a large change in injector pulse width. We're going to add a bunch of fuel, but we're only going to be doing that over a very brief period of time. Acceleration enrichment allows us to do this. So we have a bump in the injector pulse width within fractions of milliseconds, and then we decay it away and take it out because we don't want that additional fuel being added and hanging in as we're doing our normal part throttle driving. So let's say we're driving part throttle, we're at 10% throttle, all of a sudden we go full throttle. We have a very small area of time where we could have a momentary lean condition. So we're just gonna ramp the pulse width up real quick. We add the pulse width to the base values from steady state from our table, and then we'll find that we have the proper fueling. And then as soon as we have that event ends, the pulse width goes right back to wherever it would be within the table. So it's a momentary increase with the acceleration enrichment. But the important thing to take away from this is that the main fuel table characterizes the steady state airflow and the steady state operation. We have to make sure the main table is dialed in 100% before we even think about touching the acceleration enrichment. One thing that I find when I'm looking through calibration files from students and from even other tuners, a lot of times people complain about the drivability problems with the vehicle, or they're complaining that there's something wrong. They give it some throttle, there's kind of a hesitation and a lag. That is almost always a result of the acceleration enrichment being incorrect. But what I see, one of the most common things I see, is that the main fuel table isn't dialed in correctly. So for example, if we're driving in the part throttle, and you're seeing that in steady state conditions, that your closed loop correction, for example, here is taking out 14%. Well, that means that your base table here has too much estimation of airflow, or the traditional mode, the values are simply, the percentage values are just simply too high. So we want to make sure before we even attempt to look at the acceleration enrichment that we've dealt with our main table here in all conditions. If your injector pulse width is incorrect in your base, the acceleration enrichment is simply going to be adding on to the values. So if you have essentially bad data from your table and you have a transient event and you're finding that there's a stumble or hesitation, chances are the acceleration enrichment is just applying itself on top of a poorly tuned main table. So very important to understand the main fuel table has to be dialed in. The other important aspect here is that the main table represents the engine in its warmed up state. So meaning we're at 160 degrees Fahrenheit or higher in our engine coolant temperature. We're getting proper atomization out of the fuel injector. It's very important to understand this because when a cold engine, we have to use warm-up enrichment and some compensation tables. We've talked about that in our cranking, post-start, and warm-up enrichment tutorial, talking about how these are applied and why these are important. What we have is a wall wetting effect where it's always in place. So as we spray our fuel into our intake track, into the engine, some fuel is not going to make its way into the engine. It's going to be sticking to the intake track as a fuel film. In this situation, if we're warm condition, injector's atomizing properly, there's always going to be some fuel film present in the intake track for each engine cycle, but we can account for that fairly easy. When we're talking about a cold engine, the atomization of the injector is poor. The droplets of the fuel spraying out of the injector are more likely to stick to the intake track and to the intake valve. So each engine cycle, if we're on a warm engine, we're calibrating everything, we have proper fueling delivery, everything is good. On a cold engine, all of a sudden, we're starting to run lean. That's because each engine cycle, we're coming up short by having no additional fuel added for our wall wetting effect on a cold engine. Thanks for checking out our teaser clip. If you want to see the rest of this video and more than 500 hours of current EFI training we have to offer, make sure you click right here. If you want to go and check out more teaser clips from this training course, click here, and you don't want to miss any of the videos we're going to be releasing on this channel, so make sure you subscribe and click here. Thanks for watching, and I'll see you guys later.